All right, so now that we've done all of the theory with virtually every kind of spectroscopic technique that will require you to master this semester, let's look at how we solve for structure, because this is going to be the bottom line skill that you're going to have to master and exhibit on your next exam. I think there are some true and tried methods that we can employ every time we do a particular problem. The first one that I would do is, if you are not given the molecular formula, the first thing I would look at is the mass spec. And on the mass spec, there are several things that we want to try and determine. We want to look at the number of carbons. Now, on some problems, we may not be given enough data to do this. Do I have a bromine or a chlorine? Remember, a bromine would be an M and an M+2 peak in a 1-to-1 ratio, where the M is just a little bit taller than the M+2. For chlorine, the M and the M+2 is in a 3-to-1 ratio, with the M being the larger of the two. Can also look for sulfur. That's going to be in a ratio of 100 to about 4. And of course, we can also look for oxygen. This is often very difficult to spot because the second peak is so small. So you're looking at a ratio of 100 to less than 1. And again, we won't see this demonstrated very often. These are 3 great things to look for on the mass spec. Now let's switch our attention to the FTIR for a moment. So on the FTIR, if I'm doing a spectral problem, there are some peaks I'm always going to look for. I'm always going to look for an OH stretch. If I see an OH stretch from about 3200 to 3600, I'm going to suspect an alcohol. If I see a stretch that's broader and wider, let's say 3500 to 3300, and I see a carbonyl stretch at 1680 to 1720, I'm going to suspect a carboxylic acid. Now there are some other characteristic peaks that we want to look for, but I want to have an emphasis here on simplicity. It is certainly true you can look for a stretch between 33 to 3400 and look for a nitrogen-hydrogen stretch. You could look for an alkyne carbon-hydrogen at 3300, that's moderate. You could look for an alkene or an aromatic at 3100, that's weak. But rather than bogging yourselves down with a whole lot of detail that you need to remember, I would focus on being simplistic. And so what I would like to do for you at this time is to look at a couple of very simple examples and to apply these first two steps. So what we're going to do is take a look at a spectral problem. One that's not too terribly difficult. And I simply want us to look at the mass spec. And so as we look at the mass spec, I want you to notice that I have a region see if I can copy and paste this. Doesn't look like it will let me, but I might be able to select all and then copy. Let's see how clever I can be today. It will not allow me to paste, so I can't be very clever. So let's just go back and look at this mass spec again. And I would like for us to focus on the M and the M+2 peak that is in a 3:1 ratio. That signifies I have a chlorine atom. Now, we're already given the formula. When you're given a formula, the first thing that you want to do is calculate the degree of hydrogen deficiency. And in this case, the hydrogen deficiency is going to be 0. Again, 2m+2 would be 8, minus 7, minus 1 is 0 divided by 2. There are no rings, and there are no multiple bonds. So we're looking at an alkyl group that has an oxygen and a chlorine. First thing we want to look for is that oxygen an alcohol, or is that oxygen an ether? Because those are really the only two functional groups that it could possibly be. So let's go back to what we know after looking at the mass spec. So once we have looked at our mass spec, we now know that we have a formula of C3H7OCl. The degree unsaturation is equal to 0. So we could have an alcohol. We could have an ether. And it's going to be one of these two. Can't have a carboxylic acid because I don't have enough oxygen atoms. And it can't be an ester. I don't have enough oxygen atoms. So it's going to be one of these two. And also, is the chlorine going to be integrated in a primary position or in a secondary position? So to answer these questions quickly, we simply want to take a look at the IR spectrum. So let's do that. And in the IR spectrum, notice that there is absolutely no OH stretch. We've answered the first important question. We have an ether. An ether, you get that or you don't. Oh my gosh, here I go again. I'm so clever, so witty. They should make a Broadway show starring me. It should just be the Doc Oz show. That'd be sweet. All right, so I have an ether. And now the question is, what does this carbon skeleton look like? Is it a carbon and an oxygen and a carbon and a carbon? Probably that's going to be our only possibility. And will the chlorine be here? Will it be here? Or will it be here? To get some ideas on this, we simply need to look at the proton NMR. So notice what we've done. We've started with mass spec. We know that there's a chlorine atom. We look at the formula. We know the degree of saturation is 0. We've looked at the IR. We know that most likely we have an ether. Now it's time to look at the proton NMR. And when we expand the proton NMR, I have 3 hydrogens that integrate as a singlet. That's certainly going to be a methyl group, either bonded to a carbonyl or in this case, a heteroatom. So again, let's stop right there. I have a CH3 bonded to a heteroatom. Chlorine's only going to make 1 bond, so that CH3 is most likely bonded to an oxygen atom. And so we can begin to give a little detail to our structure. And we can now discount the chlorine being on this terminal methyl group. That eliminates one of my 3 possibilities. And of course, I'm going to have a carbon and a carbon. Is the chlorine bonded to carbon number 1 or to carbon number 2? Answer this question again. Let's look at the proton NMR. I have 4 hydrogens that are nearly equivalent. You'd be really tempted to say that these 2 hydrogen environments are equivalent. And let me tell you what I think is going on here. I think that you're going to have 2 methylene hydrogens bonded to an oxygen and 2 methylene hydrogens bonded to a Cl. They have about the same chemical shift. So you have overlapping peaks, and my prediction is that these coupling constants, if we could actually see them, would not be equivalent. So going back to our possibilities, I think we can choose the chlorine atom is on carbon number 2. And so we'll have something that looks like this. I want to take the time to circle my heteroatoms, the chlorine, and the oxygen. We'll call these 3 hydrogens HA, and they should be a singlet because that carbon is bonded to a heteroatom. We will call these 2 methylenes B, and this should actually be a triplet. Finally, HC, they should also be a triplet. So in terms of signals, triplet, triplet, and singlet. And we can certainly go back and check our NMR. And what is likely is that we have a triplet and a triplet that are so close to overlapping this looks like a multiplet. If this hypothesis is true, I should have 3 different carbon environments. And I do. I have what is called a triplet. I have a triplet. And I have what is a quartet. And what must be happening with the quartet is you're seeing some strange coupling with that oxygen atom. So the structure that is most consistent with all of this data is the one that we've proposed. In fact, if we were to name this molecule, we would name it 2-chloro, 1-methoxyethane. 2-chloro, 1-methoxyethane, all one word. And this would be our solution. So we've justified all of the NMR data, both proton and carbon, all of the mass spec data, all of the FTR data, and the elemental analysis from which we get the empirical, and in this case, the molecular formula. So this is how we want to approach this problem. Let's take a look at one that has very similar characteristics, and let's just see how our conclusion might change. Notice I have the exact same formula. So of course when I go to the mass spec, I have an M and an M plus 2 and a 3-to-1 ratio. That's really difficult to see unless you blow this up. Looking at the IR, I clearly have an OH. So now I have an alcohol. Let's go to the proton NMR. And there are 2 triplets, like real nice triplets. There is what we can safely assume is a multiplet that integrates as 2 hydrogens. And of course, we see that we have 1 hydrogen. Of course, that's going to be the one that exchanges. This is the characteristic broadening that is associated with an alcohol. And if we take one last look, our 2 triplets are furthest downstream. So we have a CH2, a CH2, a CH2, and OH. Of course, this is going to be our deuterated chloroform. It's not showing it. It's at about 7.3. I think we're ready to propose a structure at this point. So putting all of this together, carbon, 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 Cl, OH. I'll call this hydrogen HA. These 2 will be HB. Of course, these will be HC. And finally, these 2 will be HD. Now let's begin to look at what we have. In magenta, I will have a triplet. Now, the chemical shift by being bonded to chlorine is going to be real similar to the chemical shift bonded to this OH. And so HB should also be a triplet. I would expect the one bonded to the oxygen to be a little bit more downfield. But both of these are going to be triplet signals. And of course, in red, you're going to have a triplet of triplets, which is 9 peaks. And it's probably going to look like it's 5. So it's going to look like a quintet. And this peak should be the furthest away, the furthest upfield. So if we were to actually place these in order, I would suspect this would be the most downfield, followed by the chlorine, followed by the multiplet. Again, this really isn't 5 peaks, but the peaks are going to overlap, and the low resolution of our spectrophotometer is going to, our spectrometer is going to be not sufficient enough to give the kind of splitting that this should have. So let's go back and look at the proton NMR. And again, we see the two triplets. One's at 3.8 to 3.85, one's at 3.68 to about 3.72. That is, according to our prediction, our multiplet between 2 and 2.05. And carbon NMR should have 3 kinds of carbons, and we do. And again, the one in the middle is going to be due to the fact that it is 2 carbons away from both the oxygen and the chlorine. So this is consistent with the structure that we have proposed. Let's go ahead and name this guy. We are going to have 3 chloro, 1 propanol. 3 chloro, 1 propanol. Now, just to tie this lesson, since we're about at the end here, so these are 2 really good examples of how you can solve for NMR structures. Let's tie this kind of all together and look at something that's pretty interesting, and that is conformation. So what I want to do see if we can find 3 chloro, 1 propanol. And we do. So I'm going to download this molecule. And so this renders this molecule in a stick figure similar to what it would look like if you were to build this using a model kit. And one of the things that we're going to be dealing with this week is looking down the axis of a bond. For example, let's imagine we look down the C1, C2 axis. So you would rotate this molecule so that you can no longer see this bond. And there's lots of different ways we can do this. But as we look down the bond, we can see 3 groups that are bonded to carbon 1. We have an OH, a hydrogen, and a hydrogen. And on the back carbon, we can see that there are 2 hydrogens and, of course, a CH2Cl. The 2 biggest groups on these 2 carbons, on the front carbon, it's the OH. On the back carbon, it's the CH2Cl. We want the 2 biggest groups to be as far apart as possible. And so we see that that is indeed the case, because we have the OH and we have the CH2Cl at 180 degrees apart. This kind of projection is called a Newman projection. And I would like to draw this molecule for you showing this type of dimensionality, but now it'll be on a 2-dimensional surface. So the front carbon is simply rendered as a dot, while the back carbon is rendered as a circle. And on this front carbon, of course, drawing this straight is often a challenge. we had an OH, a hydrogen, and another hydrogen. So notice we render what is bonded to the front carbon by actually seeing these bonds intersect with the dotted carbon. And just to emphasize this carbon, I'm going to render it in green. Okay. On the back carbon, we show it's bonded by not intersecting to the dotted circle. And of course, here we see the CH2Cl, the hydrogen, and the hydrogen. When we have a conformation where the two biggest groups are anti to one another, again a 180-degree bond angle, this is called an anti-conformation. Anti-conformation means the dihedral angle, which is an angle between four atoms. So we're talking about the C and the CH2Cl to the back carbon, to the front carbon, to the OH. So the CH2 is going into the plane, and it's bonded to a back carbon, and then a front carbon will be popping out at you, and then of course the OH would be coming out of the plane. That would be 180 degrees relative to the C and the CH2Cl and the OH. This is a low energy conformation. We can rotate these bonds around these carbons, and every 60 degrees we will, if the molecule is asymmetric, generate a new conformation. Let me show you the one that's going to be the highest in energy. Again, here's my front carbon. Here's my back carbon. I'm going to hold the front carbon steady and then slowly rotate the back carbon. Again, this can sometimes be difficult to render on the screencast because it really requires a lot of precision. But the more you work at this, the better you'll be able to draw these artistically. And when the largest groups have a zero dihedral, we're going to call these eclipsed. So remember, we have an OH, and then now we have a CH2Cl. These biggest, bulkiest atoms are going to clash with one another. And at all other positions, we have hydrogens. Of course, this electronic repulsion is going to cause what we call steric strain. So anyway, this is the eclipsed conformation. It's very high in energy. It has a dihedral between the biggest, bulkiest atoms of 0 degrees, and this is the highest energy conformation. And we'll also learn about some other conformations where we have gauche interactions. Those are dihedral angles of 60 degrees. So this is what awaits us Monday in class. We'll also be talking about the strain energy in ring systems, and particularly stable conformations of cyclopentanes and cyclohexanes. So I will be posting tomorrow an additional screencast that goes into more depth regarding these conformations.